Elixir guides, GenServer. In the previous chapter, we used agents to represent our buckets. In the first chapter, we specified we would like to name each bucket so we can do the following: create shopping, put shopping milk 1, get shopping milk. In the session above, we interacted with the shopping bucket. Since agents are processes, each bucket has a process identifier, PID, but buckets do not have a name. Back in the process chapter, we have learned that we can register processes in Elixir by giving them atom names. So agent, start link, the initial state, name, shopping. Then KV bucket, put shopping milk 1. KV bucket, get shopping milk. However, naming dynamic processes with atoms is a terrible idea. If we use atoms, we would need to convert the bucket name, often received from an external client, to atoms, and we should never convert user input to atoms. This is because atoms are not garbage collected. Once an atom is created, it is never reclaimed. Generating atoms from user input would mean that the user can inject different names to exhaust our system memory. In practice, it is more likely you will reach the Erlang VM limit for the maximum number of atoms before you run out of memory, which will bring your system down regardless. Instead of abusing the built-in name facility, we will create our own process registry that associates the bucket name to the bucket process. The registry needs to guarantee that it is always up to date. For example, if one bucket process crashes due to a bug, the registry must notice this change and avoid serving stale entries. In Elixir, we say the registry needs to monitor each bucket. We will use a GenServer to create a registry process that can monitor the bucket processes. GenServer provides industrial strength functionality for building both servers in Elixir and OTP. Our first GenServer. A GenServer is implemented in two parts: the client API and the server callbacks. You can either combine both parts into a single module, or you can separate them into a client module and a server module. The client and server run in separate processes, with the client passing messages back and forth to the server as its functions are called. Here we'll use a single module for both the server callbacks and the client API. Create a new file at lib.kv registry.ex with the following contents. So def module kv.registry and use GenServer. Then we have the client API with start link, which starts the registry. We have lookup, looks up the bucket PID for name stored in server. Create ensures there is a bucket associated with the given name in server. Server callbacks, init, handle call, handle cast. The first function is start link 1, which starts a new GenServer passing 3 arguments. 1, the module where the server callbacks are implemented, in this case, the current module. 2, the initialization arguments, in this case, the atom OK. And 3, a list of options which can be used to specify things like the name of the server. For now, we will forward the list of options that we receive on start link 1, which defaults to an empty list. We will customize customize it later on. There are two types of requests you can send to a GenServer: calls and casts. Calls are synchronous, and the server must send a response back to such requests. Casts are asynchronous, and the server won't send a response back. The next two functions, lookup to and create to, are responsible for sending these requests to the server. In this case, we have used lookup name and create name respectively. Requests are often specified as tuples like this in order to provide more than one argument in that first argument slot. It is common to specify the action being requested as the first element of a tuple and arguments for that action in the remaining elements. Note that the requests must match the first argument to handle call 3 or handle cast 2. That's it for the client API. On the server side, we can implement a variety of callbacks to guarantee the server initialization, termination, and handling of requests. Those callbacks are optional, and for now, we have only implemented the ones we care about. The first is the init1 callback that receives the second argument given to GenServer startLink 3 and returns OK state, where state is a new map. We can already notice how the GenServer API makes the client-server segregation more apparent. StartLink 3 happens in the client, while init1 is the respective callback that runs on the server. For call to requests, we implement a handle call 3 callback that receives the request, the process from which we receive the request, _from, and the current server state names. The handle call 3 callback returns a tuple in the format reply new state. The first element of the tuple, reply, indicates that the server should send a reply back to the client. The second element, reply, is what will be sent to the client, while the third, new state, is the new server state. For cast to requests, we implement a handle cast to callback that receives the request and the current server state names. The handle cast to callback returns a tuple in the format no reply new state. Note that in a real application, we would have probably implemented the callback for create with a synchronous call instead of an asynchronous cast. We are doing it this way to illustrate how to implement a cast callback. There are other tuple formats, both handle call 3 and handle cast 2 callbacks may return. There are also other callbacks like terminate 2 and code change 3 that we could implement. For now, let's write some tests to guarantee our GenServer works as expected. Testing in GenServer. Testing in GenServer is not much different from testing an agent. We will spawn the server on a setup callback and use it throughout our tests. Create a file at test.kv registry test.exs with the following: def module kv registry test, use xunit case async true. Then we have the setup, we make a new registry, start supervised kv registry, we're grabbing it here. Our test should pass right out of the box. There's one important difference between the setup block we wrote for the kv registry and the one we wrote for kv bucket. Instead of starting the registry by hand by calling KV registry start link 1, we instead called the start supervised 1 function, passing the KV registry module. The start supervised function will do the job of starting the KV registry process by calling start link 1. The advantage of using start supervised is that XUnit will guarantee that the registry process will be shut down before the next test starts. In other words, it helps guarantee the state of one test is not going to interfere with the next one in case they depend on shared resources. When starting processes during your tests, we should always prefer to use start supervised. We recommend you change the previous setup block in bucket test.exs to use start supervised too. If there is a need to stop a GenServer as part of the application logic, one can use the GenServer.stop1 function. The need for monitoring. Our registry is almost complete. The only remaining issue is that the registry may become stale if a bucket stops or crashes. Let's add a test to KV registry test that exposes this bug. Removes buckets on exit. So we create, and then we look up, and then we stop the bucket, and then we look up again, and we get an error. The test above will fail on the last assertion as the bucket name remains in the registry even after we stop the bucket process. In order to fix this bug, we need the registry to monitor every bucket it spawns. Once we set up a monitor, the registry will receive a notification every time a bucket process exits, allowing us to clean up the registry. Let's first play with monitors by starting a new console with IEX S mix. So we start a link, we gonna monitor this PID, agent stop PID, and then flush. Note process.monitorPID returns a unique reference that allows us to match upcoming messages that monitoring reference. After we stop the agent, we can flush 0 all messages and notice a down message arrived with the exact reference returned by monitor, notifying that the bucket process exited with the reason normal. Let's re-implement the server callbacks to fix the bug and make the test pass. First, we will modify the GenServer state to 2 dictionaries, one that contains name PID and another that holds ref name. Then, we need to monitor the buckets on handlecast2 as well as implement a handleinfo2 callback to handle the monitoring messages. The full server callbacks implemented is shown below. So def init, now we set names and refs to 2 maps. And we handle call. Handle cast. Handle info down. Then we're gonna remove that ref. Observe that we were able to considerably change the server implementation without changing any of the client API. That's one of the benefits of explicitly segregating the server and the client. Finally, different from the other callbacks, we have defined a catch-all clause for the handleinfo2 that discards any unknown message. To understand why, let's move on to the next section. Call, cast, or info. So far, we have used 3 callbacks: handle call3, handle cast2, and handle info2. Here's what we should consider when deciding when to use each. Handle call 3 must be used for synchronous requests. This should be the default choice, as waiting for the server to reply is a useful back pressure mechanism. Handle cast 2 must be used for asynchronous requests, when you don't care about a reply. A cast does not even guarantee the server has received the message and, for this reason, should be used sparingly. For example, the create2 function we have defined in this chapter should have used call2. We have used cast2 for didactic purposes. Handle info2 must be used for all other messages a server may receive that are not sent via GenServer.call2 or GenServer.cast2, including regular messages sent with send2. The monitoring down messages are such an example of this. Since any message, including the ones sent via send2, go to handle info2, there's a chance unexpected messages will arrive to the server. Therefore, if we don't define the catch-all clause, those messages could cause our registry to crash because no clause would match. We don't need to worry about such cases for handle call 3 and handle cast 2 though. Calls and casts are only done via the GenServer API, so an unknown message is quite likely a developer mistake. Check out this cheat sheet. Oh no. Monitors or links. We have previously learned about links in the process chapter. Now with the registry complete, you may be wondering when we should use monitors and when we should use links. Links are bidirectional. If you link two processes and one of them crashes, the other side will crash too, unless it is trapping exits. A monitor is unidirectional. Only the monitoring process will receive notifications about the monitored one. In other words, use links when you want linked crashes and monitors when you want to be informed of crashes, exits, and so on. Returning to our handle cast 2 implementation, you can see the registry is both linking and monitoring the buckets. This is a bad idea, as we don't want the registry to crash when a bucket crashes. We typically avoid creating new processes directly. Instead, we delegate this responsibility to supervisors. As we'll see in the next chapter, supervisors rely on links, and that explains why link-based APIs, SpawnLink, StartLink, etc., are so prevalent in Elixir and OTP. Alright, gonna start the next chapter. I'll be right back.